A very good morning to you all. So we'll be talking about the model number 5, the deflection of beams. Here, as part of the VT syllabus, we'll be talking about moment curvature relationship, which we have learned in model number 4 in the column chapter. Like that, we'll be talking about assumptions made in this deflection theory, as well as we'll be talking about the how to find the deflection and the slope for a cantilever beam, as well as for simply supported beam, as well as for an overhanging beam subject to point load as well as uniformly distributed load by two methods. One is called the double integration method and the Maclaurin method. So these are two methods what we'll be talking now. Now coming to the definition of a deflection. What is a deflection? The deflection is measured from the virginal neutral axis to the deformed shape of the beam. This is called as a deflection. The displacement y is defined as a deflection of the beam, and coming to the deflection, generally the maximum deflection comes in the center, and at this the angle is called as slope. Generally in case of for the structural designer, we'll be talking about the permissive deflection is equal to length of the beam divided by 300. This is a y max. So after talking about what is meant by deflection, there are two methods of determining deflections by double integration method, moment area method, Maclaurin method, all we have. But in our syllabus we have only double integration method. Now what is the deflection double integration method? The deflection curve of a beam, which we learned in the model number 4, this is called Euler's differential equation. I d square y by dx square is equal to m, and this is called as deflection and is called as slope. Hence this whole part is called as the Euler's differential equation. Ei d square y by dx square is called as mx is called as an differential equation of deflection. With this, we integrate the first equation, then we get the slope equation. Once again, if I integrate the same equation, I get the deflection. So let us try to understand how do we get this slope equation as well as the deflection equation by a small example. So before talking about that, we have to talk about something called as sign conventions. So what are the sign convention? We tell for sagging moment is positive and for hogging moment is negative. The same with assumptions and limitations of deflection caused by the shearing action negligibly small compared to the bending. Deflections are small compared to the cross-section dimension, hence it can be ignored. All portions of the beam are acting on the elastic range, as well as the beam is straight parallel to the application of the loads. So this is assumptions and the limitations, and this is called as the introduction to the chapter, where we talk about bending moment and as well as shear force, and it's called strength criteria as well as the stiffness criteria of a beam. Now, under the action of external loads, any beam bends and suffers deflection at various points along the length of the beam. The deflection is caused by the bending moment acting at various sections of the beam, and the deflection also caused by the shear force, but the magnitude is very small compared to that the bending, and hence it can be generally neglected. So let us now try to define what is meant by a deflection as well as the elastic curve. Elastic curve is also called as a deflection curve. Hence, the deflection is defined as the vertical distance in transverse direction between positive positions of axis before and after loading at the section of the beam, defined as a deflection of the beam. The same way, the deformed shape of a beam is called an elastic curve or a deflection curve. Here, also it can be defined as the neutral axis in its deflected position after loading of the beam is known as elastic curve or deflection curve. As well as the slope, as I told you, the slope of a beam at any section is defined as the angle of inclination of the tangent drawn to that section to the axis in its deflection position after loading, measured with respect to the undeformed axis. So that I shall define you later in a numerical example what do you mean by slope. And the product of the mode of elasticity and the moment of inertia is called as flexural rigidity. Now coming to the Euler's differential equation, we know that this is the equation what we have here, where EI is called as the flexural rigidity and M is called as moment at a section. Now when we do a derivation, we talk of assumptions of which are made in the diffraction. This will be asked for 5 marks in the examination for you. So hence you have to define by this axis of beam is horizontal before the loading, diffraction to the shear force is negligible, and simple bending equation is equal to m by I, which we learned in the third module. That should be applicable in the here. Material of the beam is homogeneous, isotropic, and obeys Hooke's law. The modulus of elasticity is same in compression as well as in tension. Plane section remain plane before and after bending. So this is assumptions what to be stated in the problem. So however, as part of a syllabus you don't have an derivation part. Anyhow, I have included in this slide how the derivation has come. So this you can skip it out. So here this is small picture represent what do you mean by slope. This angle is called as a slope and is called as y, called as diffraction. So various methods of finding slope and diffraction of double integration method as well as Maclaurin's method what we have in our syllabus. Now in the same regard, how do we get an slope as well as a diffraction? The first step in the problem is to write the Euler's differential equation EI d squared y by dx equals mx6. Now integrate this equation with respect to x. Hence EI dy by dx m into dx plus c1, where c1 is called as constant of integration. In a similar way, once again integrate with respect to x, the both sides we get c1 and c2 are called as constant of integration. This can be calculated or evaluated by applying the boundary conditions of a beam here. Now what I told that these are called as two constant of integration which can be known by applying the conditions of diffraction and the slope at the supports. So we'll go into the how do I find out. For the first case we'll try to understand, determine the slope and the diffraction for a beam loaded as shown in the figure. Find the maximum diffraction and the slope. Hence this is a fixed support, this is a beam subjected to a point load. Whenever beam is subjected to a point load, then this tries to bend. That is called as an elastic curve. And now coming to this elastic curve, the slope at this fixed end is 0 and the diffraction is also 0. The similar way at this point at the free end the diffraction is maximum as well as the slope is also maximum here. Now how do I write the bending equation here? So this is a problem given where your job is to work out what is the deflection when a point will be subject to 6 kilonewton with the length of the member is 3 meters, Young's model is given and I is given. And first we'll write down the equation for bending moment. As we know that hogging bending moment is negative, hence moment. What is moment? Force in perpendicular distance. Hence P into X is written here. So hence in this regard the Euler's differential equation EI d square by dx square is written as m, and the m is equal to P into X minus is written due to the hogging bending moment. Now this is equation number 1. Now this is integrate with respect to x. When I integrate with respect to x, I get an slope equation. EI dy by dx is equal to P into x square by 2 plus c1. In a similar way, the equation 2 again is integrated. Then we get an diffraction equation. EI y so P x square was there, hence it comes to x cubed by 2 into 3 becomes 6 plus C1x plus C2. Hence, at the fixed end condition at this point, the slope is 0 as well as the deflection is 0. Hence, that is called as conditions of for getting the constant of integrations. The C1 and C2 are calculated. So hence, applying the conditions here, we get the value of C1 is equal to PL square by 2 and x is equal to L. Again, that the fixed end, we have the difference is 0, apply the 0, then we get the value of C2 is equal to PL cubed by 2. Now, substitute these values of C1 and C2 in the equation here, and then when I get the equation, we get when x is equal to 0, you have the maximum equation, that is the maximum slope and the maximum deflection. Hence, we get PL cubed by 3EI as well as the slope is equal to PL squared by 2EI. That means to say in the problem, I'll just show you the pictorial representation. So here x is equal to 0, at x is equal to L at this point, the slope is 0 and the deflection 0. At x is equal to 0, you have a maximum deflection and the maximum slope in the problem. So that's what is substituted here. Based on that, you'll be getting the two constant of integration, and then you sub equation and you'll get the slope is equal to PL square by 2EI. Substitute the value of P L given in the problem, 2EI with and the conversion. So it was given as 6 kilonewton. So hence convert into Newton, 6 into 10 cube into the L. L was given 3 meters. Convert into mm, hence 3 into 10 cube square divided by 2 into the fractional rigidity EI. Young's model is given as I. Substitute that, we'll be getting in 8.0357 for 10 raised to minus 5 radian. The same way, we'll be talking about the substitution of deflection. Calculate that as 0.161 in the equation. So this problem is application to the cantilever beam subject to a point load. The same way, we have another problem when the cantilever is subject to an uniformly distributed load for entire span, and A is called at the origin. Take A as a section XX, distance of X from A. Now, the moment at a distance X from A is equal to, when I take a section, W into X by 2. Hence, I get Wx squared by 2 in this problem. As it is an Hawking moment, it is minus. Hence, substitute that mx is equal to Wx squared by 2. And now you integrate this equation. I'll be getting Wx cubed by 6 plus C1 in the equation here in this problem. In a similar way, we'll be applying the boundary conditions. X is equal to L and the slope is 0 at that point. And that means say at the support the slope is 0 in case of an cantilever beam at the support. So hence substitute that, and same way the deflection is also 0. So you'll be getting the value of C1 and C2 in this problem. Once I get C1 and C2, applying the boundary condition at x is equal to L and y is equal to 0. Then you'll be getting C1 and C2. Hence you'll be getting equation EIy is equal to and WL to the power of 8. If a numerical value is given of W, L, you can substitute the equation and calculate the maximum deflection. So this problem is application to an cantilever beam problem subjected to an uniformly distributed load, as well as we found out the slope and we can find out the deflection and slope here. This is the equation. So this is a method of working out an numerical problem with a cantilever beam subjective and point load as well as an UDL. Now coming to the last problem for the day, case number 3, when simply supported beam is subjected to a single constant load at mid-span. Hence, when the point load is there, the reaction of the two supports will be half of that, so hence P by 2. Hence, if I take a section here, P by 2 into X is the moment. Hence, it is written here, moment is equal to P by 2 into X. Now, write down the Euler's diffraction equation, EI d square y by dx square is P by 2 into X. Now, integrate this equation now. Hence, when I integrate this equation now, I will be getting P by 2 x square by 2 plus C1. And due to symmetry, at x is equal to L by 2, at this maximum diffraction where you have the slope is 0. Hence, substitute that here and find out the constants of C1 and C2 in the equation. Hence, when I substitute, then I get C2 is equal to 0 and C1 is equal to PL squared by 16. So with that regard, you have got C1 and C2 in this problem. So substitute that in this problem, and once you get C1 and C2, it will be getting the maximum diffraction is equal to PLQ by 48 AI, as well as the maximum slope is equal to WL square by 16 AI. So such kind of problems, derivation subject to point load, we have done today, and problem on point load for a cantilever beam, then uniform distributed load for a cantilever beam, as well as a point load for simply supported beam problem. So this is the next problem. So this we shall talk in the next class. So I'll end up for today's lecture of understand the problem. And still if you have doubts, you can call me on my mobile. Have a good day. Stay back home. Stay safe.